All right, hello world. So I've had this book for a couple of years. I've done sort of the first handful, maybe the first 30 problems in the past, but I thought maybe I would stream every couple days and, you know, sort of document my trying to do all these problems. The thing is, this is a huge book. So this is a book called Problems and Theorems and Analysis by Pólya and Szegő. It's actually 2 volumes. This book has about 700 questions in it. Here you go. Don't expect you to be able to read all this, but there's 3 parts in this book. First one is on series. Part 2 is on integration. Part 3 is on complex variables. And then there's another 5 parts in a second volume that I also have. So I thought I would, maybe so I don't get bored because it's going to take a long time. It's going to take me pretty much years to get through all of this. I figured I would bounce around. So I'll do some of part 1, and then, on another day I'll do some of part 2, and then another day I'll do part 3, and we'll keep rotating like that. So yeah, I'll probably only be on for an hour today. But this will be day 1 of me trying to learn Polya and Szego. So anyway, this is a fantastic book. But at something like 750 problems in each volume, it's going to take a long time to get through. But the nice thing is, there's answers in the back. There's solutions. They don't always, sometimes they're not fully explained, so even with the solutions, it still takes some effort to, understand what he's saying, but, it's pretty handy. So, alright. Here's a look at, let's see if you can read this at all. There we go. So here's the first few problems. So the first question is, well, anyway, before I even get into that, I'll attempt these, for a few minutes, and then, I won't spend a lot of time. I'll spend 5 or 10 minutes trying to do them. If I get stuck, I'll look at the solution and then work through that, and then continue. So I'm not gonna waste a half hour on a problem if I don't know how to do it. But this first one I've definitely done a few times. The question was, in how many ways can you make change for $1? So you're trying to make 100 cents using pennies, nickels, dimes, quarters, and half dollars. The second question actually shows you an equation that is obviously what you're going to be using, but it has, I don't know if I'd say it, I don't know if it speeds up your computation, but it sort of it shows you how to generate solutions, but you still have to count them. So in this first one, I'm saying how many ways can you make change? You're doing something like trying to solve this equation. So you have integer, you're sort of counting up the number of ways to have integer solutions, or really natural number solutions. to this equation. I could have just said natural numbers, but you know, including 0. And it's a big number. A computer can do this in a couple seconds. It's really much faster to do it with a computer, but yeah, here's how I would do it. I would split it into two. First of all, you have h equals 2 as a solution. You're just done immediately. So 0, 0, 0, 0, 2 would work. But if you don't do 2, you could do h equal to 1, and then figure out all the ways to make another 50 cents. So it's a fairly recursive problem. So I'll do h equal 1 here, have a bunch of answers, and then I'll go over here and have like the h equals 0 case. Something like that. So if h is 1, you've still got 50 cents to go. You could have 2 quarters. You could have like 1 quarter, and then you still have to make another 25 cents out of that. So maybe I'll do that right now. Q could be 1. So like here's a solution, here's a solution. And then if h is 1 and q is 1, you've got 25 cents left to go. So you either have 2 dimes and a nickel, things like that. 2 dimes, 5 pennies. So if you do have 2 dimes, you're going to either need 1 nickel or, you know, something like that. Or you could have 0 nickels and 5 pennies. Okay. Another branch would be that you have only 1 dime. In that case, you're going to have, let's say, like 15 cents worth, right? So you could have 3 nickels, no pennies, or you could have 2 nickels, or you could have 1 nickel. So you can see it gets a little quicker. Yeah, 15 cents, right? So 1 dime with another 15 cents. 1 dime with, this will be 10 pennies, or you can have all 15 pennies. So this last solution is, you know, a $50, a quarter, a single dime, no nickels, and 15 pennies. And that's like this chunk of answers right there. And then finally you could have a quarter, you could have no dimes. If you do that, then all 5 nickels are going to that 25 cents. You could have 4 nickels, you could have 3, 2, 1, or 0. You get the idea. And obviously this would be P is 0, P is 5, 10, 15, 20, 25. So there's another block of solutions. I guess that's it. So then the last case would be we did 2 quarters, we did 1 quarter. If you had no quarters at all, but a single $50, then you still have 50 cents to go and you're not using quarters. So you could have 5 dimes, you could have 4, but if you do that, you're going to need to like make up the other 10 cents somehow, right? So you'll have either 2 or 1 or 0. There's 3 ways to do that. So there's like 1 way to have this situation with 5 dimes. There's 3 ways to have 4 dimes. It's kind of predictable at this point. You're going to have 5 ways to do this, right? So if there's 3 dimes, you want 20 more cents. I guess that's 4 nickels. or 3, or 2, or 1, or none. So there's another block of answers that correspond to having 3 dimes. 2 dimes. I mean, I don't know if we really need to even write all these out. You can see the pattern. There's 3 here, there's 5 there, so there's going to be 7 here, and there's going to be 9 in the next one. So it's like 7, 9, 11 are the last batches. But I'll go ahead and do it out. So this would be 6 nickels to make up for the 30 cents that's missing. Or 5, 4, 3, 2, 1, 0. If you have 1 dime, well, not finally, but if you have 1 dime, this is starting at 8 this time. 7, 6, 5, 4, 3, 2, 1, 0. And then finally, if you have no dimes, we have a single $50, we have no quarters and no dimes. Then the other 50 cents has to come all from nickels or pennies. We start at 10, we go down to 0. So this is a block of 11 items. This was 9, this was 7. Okay. So it's really just kind of an organized counting approach to doing this, to try and find the number of natural number solutions to this equation. I guess before I move on to this bigger case, we could start counting these. Like, here's one way, here's one way, and then this block where we had, 1 quarter, there's like 2 plus 4 plus 6, I presume, yeah. So that's 12 ways. And then 0 quarters, there's 1 plus 3 plus 5, but you could also just be a little more clever. What would we say? 1, 3, 5, 7, 9, 11, right? So 1 plus 10 is, 1 plus 11 is 12. 3 plus 9 is 12. 5 plus 7 is 12. So there's 3 sets of 12 right there. All right, and now to the hard part, I guess. We could go, so we said zero $0.50. That means all 100 cents could come from 4 quarters. That's one way that happens. Or it could be 3 quarters, and then you got to make up the 25 cents. I do feel like we just did that, right? We just counted 25 cents over here, so I suspect that's going to be 12 ways. If Q is 2, and we still have 50 cents to go, how many ways can you make 50 cents not using any more quarters? I think we did that also, right? We just counted that. So, I may as well believe myself, I guess. So here's like one, what do we say? Yeah, this is one way. 25 cents, I believe, is 12 ways. 50 cents is here is 36 ways. And what I didn't count was Q equal 1, Q equals 0. So we're still going to have a bunch of work to do for those 2 cases. This is, of course, 75 cents left, which we didn't count yet, using dimes and nickels. But it's a very similar thing like we did over here. And the last case would just be all 100 cents, but you don't use any half dollars or quarters. So in this chunk right here, I'll try to do counting 75 cents using dimes, nickels, pennies, right? So you could have 7 dimes, but then you're still going to need a nickel and 0 pennies, or no nickels and then, all 5 pennies. Like that, right? Those 2 cases. If you only use 6 dimes, right? 60 cents out of this is taken care of. You still need another 15 cents. That's going to give you 3 nickels, or 2 nickels, or 1, or none. Okay? And obviously the corresponding number of pennies is like 0, or 5, or 10, or 15. And that makes sense. Okay, so we got 4 cases there. If you've got 5 dimes, that leaves you with 25 cents coming from nickels. So it's like 5. I guess in the interest of space, I'm just going to change the way I'm writing this now, okay? So 5, 4, 3, 2, 1, or 0. Yep. And then if you had 4 dimes, you could have 35 cents to go, right? So it starts at 7. But anyway, there's clearly a pattern here, right? It goes up by 10 cents every time, so you're going up by 2 nickels. 3 gets mapped to n being 9. 2, there would still be 11 nickels. That makes sense. Yeah, 55 cents plus these 2 is 75 cents total. Yep. 10, 9, 8, all the way down to 0. If you use 1 dime, you'll still have 65 cents to go. Apparently that's 13 nickels worth. And finally, if you don't use any dimes, you still have 75 cents to go. That's like 15 nickels. We can count these if you want. But again, it's a little symmetric. We have 2, then 4, then 6, then 8, okay? All the way down to 16, 16 different solutions that come from having 0 for D. And you get like 16 different numbers for n and 16 different values for p. So anyway, if we add the first and the last, you get like 2 plus 16 is 18. So there's 18, 18. I guess this does split evenly, right? 18, 18. So you can just do 18 times 4, I want to say, through 3, 1, 2, 3, 4. Yeah, so like 2 plus 16, 4 plus 14, 6 plus 12. Anyway, 18 times 4 different solutions there. And then the last case would be if you don't use any quarters. So you're going to make up, if you don't use any quarters or half dollars, you're going to make up the whole 100 cents using like just dimes and nickels and pennies. So you've got 10 dimes, and at that case, you would need 0 nickels, 0 pennies. You could have 9 dimes, now you need to make up the 10 cents. I guess there's 2 ways to do that, right? You could have 2 nickels, or sorry, three ways to do that. 2 nickels, or 1 nickel, or 0 nickels, and that corresponds to like p being 0, p being 5, p being 10. And yeah, it's just going to continue in that way. So I got 20 cents missing. That would be 4 nickels worth. Or it could be 3 nickels, or it could be 2, or it could be 1, or it could be 0. N starts at 6 to 0. If D is 6, N starts at 8 down to 0. Okay? 10 down to 0. So I'll write all these out, but you can see like it's not actually that bad. This is super tedious, obviously. But I think at this stage in the book, this is literally problem 1. This is what he wanted you to do. And you could write a script to do this, obviously much easier and faster. This is basically what you're doing. It's just brute force what I did here. I'll show you in a moment. Question 2 is kind of interesting, but I don't think I hesitate to say that it's faster. I've done it using question 2's method. I'll show you in a sec what I'm talking about. Let's finish adding this up and see if I screwed it up, if I missed anything. So yeah, what is this? There's 1 way for this to happen. There's 3 ways for this. There's 5 ways for this. Okay, down to 21. So 1 plus 21 is 22. And this time it's not even. You got to be a little careful. So 1 plus 21 is 22. Again, 3 plus 19 is 22. right? 5 plus 17 is 22. But it's not even. There's 11 of these combinations, so we're going to get 5 of them. You could just do 5.5 if you want. That'll be the correct answer. But what's happening is, 0, 10, 1, 9, 2, 8, 3, 7, 4, 6, they all get matched and give you 22. But then this guy, the 5 dimes case, gets mapped to 11 cases, and it doesn't get matched with like another 11 or anything. So you're sort of, it's 5.5, or whatever this works out to be. And that is about it for this problem. If you wandered in, I'm about to add it up and give you an answer, but if you just popped in and don't know what the hell I'm talking about, I'm doing these problems one at a time through this gigantic book. And the first one is, how many ways can you make change for $1 using, pennies, nickels, dimes, quarters, or half dollars? And there's an answer in the back, so I could check my work, but I've done this one before, so I remember it. So 36 and 12 is 48, plus another 2 is 50. So we're getting 50 from the 1 or 2 half-dollar cases. There's 50 over there. And then over here, let's see, what is this? It's not quite 80, right? It's like 72. And this is 110 plus 11, so it's 121, I guess. Sure. So we're missing, there's 1 there. We got 48. I don't know, man. We're getting like 121 plus 72 plus 48 plus 1. I don't know. 80 plus 40 is 120. So here we're getting 242, I believe. And then there was 50 over here as well. So this plus 50. Oh, that's the correct answer, 292. I only know it's the correct answer because I've done this before. But if you look in the back of this gigantic tome, he's got solutions. And I don't know how well, you probably can't read this, but 292 is the answer. So yeah, 1 problem down. All right. So 2 is, let's see if I can get this to, there you go, something like that. 2 says, let n be a non-negative integer. And let an denote the number of solutions to this equation. So it's basically the equation we were just looking at. Then this series is some rational function. Express this series as a rational function is the question. So it's pretty cool. The concept is we're going to let basically solutions, the number of solutions to this equation, be the coefficients in some power series, and try to find a formula for that. Hey, what's going on, Richard Meld? I'm doing some math. I decided to put everyone to sleep. So yeah, 2 is saying let an denote number of solutions to this equation. 25u plus 50 times some of the variable v, and then you set it equal to n, And so AN will be the number of solutions. Oh yeah? Yeah, it's a nice pen. It's a Pelican. I forget if this is, it's probably like an M400, something like that. So here's how this one works. Yeah, what ends up happening is if you were to take a product of stuff like this, like say I put 1 plus, what is this, probably c or something, c plus c squared plus c cubed, c to the 4, okay, and you just keep going, like an infinite series. If you then put here powers of 5, and then in another factor I'm going to put powers of 10, but for here I'll do 5 and 10 and 15 and 20, etc. What's going to happen when you multiply these out is that you're generating different combinations of change. So like this 5 stands for 1 nickel, and when you multiply it by c cubed, that's like adding, it's going to add the 5 and the 3, but that represents 1 nickel and 3 pennies. Or if I do like 10 with 2, that's two nickels and 2 pennies. So every product that you get represents some amount of change. So I just did it with pennies and nickels, but if I keep going and do 1 plus, and of course 1 corresponds to 0 of that thing. So this is p equals 0, p equals 1, p equals 2, p equals 3, etc. This is 0 nickels, 1 nickel, 2 nickel, etc. So now I'm going to do it with dimes. And this is one that I definitely, oops, I screwed it up already. Sorry. 1 plus, and then this is going to be quarters. So here's 1 quarter, here's 2 quarters, etc. And then finally you have half dollars, 1 plus c to the 50, etc. This is one that I definitely had to look at the solution for. So if you look in the back, if we just cheat and jump right to it, he's explaining exactly what I was just saying. So this power series, where the ANs are supposed to represent the number of solutions, he just immediately gives you this answer, which I'll explain the last line in a second. But yeah, that's pretty much it. It's an easy. That's the thing. Like I would never have thought of this unless you had a class in combinatorics that specifically talked about this. So at some point I looked this up like about a year ago. I was trying to do this problem and I couldn't answer it, so I looked at this answer and I was like, oh, I see, I get it now. But yeah, when you multiply these together, you're getting things like, okay, 20 times c to the 15 times c to the 5 or whatever, and that's 2 dimes and 3 nickels and 5 pennies, that kind of combination. As for how you use this to like count the number of ways, or how would you use this to do number 1? How could you use this to like count the number of ways to get change for 100 cents? That's a whole other story. He mentions down here, if you want numerical computations of the AN, you should start, there is sort of a pattern, but do one at a time. Do like one factor at a time. So like count what it would be just from the pennies, then repeat this process, including the nickels, then do it again with dimes. So I don't know, maybe I'll do that again right now. I don't remember quite how that works out, and maybe that'll be like one of the last things I do today. But I remember it still took a long time. Frankly, the way I did it, number 1, a minute ago, I just did this for counting the number of ways to to make change for 100 cents. I just did it like brute force, like the way a computer would do it. Like I said, what if we have two $half? There's one solution. What if we have one $half? Then we could have 2/4 or 1/4 or 0/4. So this is much simpler. And actually, this wasn't really that slow. It sounds like it would take a while, but it was actually pretty quick. Anyway, unfortunately, this is not going to be much faster to do it this way. But this gives you sort of a more general solution. It gives you a way to like generate solutions. I don't know. It's interesting. It's good to know for other problems. Anyway, what was I going to say here? This is an answer. They wanted to know if I sum up, if I make a power series, what function does this equal? Is there like a closed form for this? And it's this, but that's not what they were going for. He wanted a rational function, not just. But yeah, it is actually this. What I mean is when you multiply these all out, like all 5 of these infinite series, some of the combinations, I mean, at some point there's one where the power is n. And so there is some integer number in front of that is what you're looking for. It's the number of ways to make change for n. This first chunk, this first series, it's just a power series. So it's like a geometric series. So the first one is 1 over 1 minus c. Like this series would be 1 plus c squared. That's like a Calc 2 fact. So that's what I wrote here is the first one. And then this is powers of 5, and this is powers of 10, and this is powers of 25. So each one of these, so that's where you're going to get this formula from. Like this right here is the same as 1 minus c, 1 over 1 minus c to the 5, 1 over 1 minus c to the 10, whoops, 1 over 1 minus c to the 25, and then finally 1 over 1 minus c to the 50. And that's it. That's the answer they were looking for number 2. I'm gonna go ahead because I'm kind of curious now how bad it was. Number 2, he doesn't actually ask for this. What I'm about to do is like he doesn't ask you to do anything else. He just says find this function. So we're done with that. We should move on, frankly, to other things, more interesting questions. But if you wanted to know like how does that help us find an? Like how do I answer number 1 now that I know this cool function? Well, it's still easier said than done, unfortunately. So like if I was to follow this up and say, all right, find this number. Now that you know that the sum of an c to the n is given by this, like how would I find the coefficient of one particular one of these? Can't type anything. I have my keyboard next to me. Yeah, so this is still kind of a nightmare to do, but we'll give it a shot. The suggestion in the solutions, by the way, so I just showed this to you, but I'll show it to you again. The suggestion is to just start, like do it with pennies, then do it with pennies times nickels. So go ahead and use this form that we were talking about, but sort of build up to it and see. And it mentions it's convenient to dispose the coefficients in a rectangular array. So I don't know. It's saying try to do this carefully, keep track of things. But also, since you're stopping at 100, you can just throw away all the powers that are larger than 100, of course. So yeah, I'm a little hesitant to start this one because I know this is going to be. So here's the first one. This is that first factor, and this is just the pennies. And so we get a series like this, and I just want to know the number of solutions to like the one with a power of 100. You know, when we expand all these things, I'm looking for the ones whose exponent is 100. There's only one of them in this case, but that was not very interesting. That just tells you if you're only using pennies, there's one solution to get 100 pennies. It's 100. So try this again with nickels and pennies, and I guess we'll see what happens. You're not going to like it though. So here's I'll go ahead and single out the 100 again. But here's the first factor, and then we do this again with nickels, right? 5, 10, yada yada. 100 is one of the powers of 5, and then we can stop thinking about it because these are higher than 100, so we don't care. But now you see why this sucks, right? Like, this combination, 100 pennies times 0 nickels, that gives you one way. It's conveniently the one we got back here. But if you want the rest of the ways, you're basically counting like I'm looking at every power of this 5. So I could have 1 nickel, or 2 nickels, or 3 nickels, or 4 nickels, da da da, all the way up to 100 cents worth of nickels, or what is that, like 20? So this is giving us basically 21 solutions coming from pennies and nickels combined. Right, here's the 0th case, here's 1 nickel, here's 2 nickels, all the way up to 20 nickels. So you're getting 21 answers if you only use pennies and nickels. Is this faster? I really don't think so. You know, our other way would have been to be like, you're only allowed to use pennies, and so you only get this as an answer. Or you're allowed to use nickels, so you could have 20 nickels or 19 or all the way down to 0 nickels. Like, this was faster. Just you writing down values for what n could be. It was definitely faster than thinking of it this way, I think. Yeah, I actually did this once because I wanted to just see exactly how it would work out. But I'm starting to think this is a stupid idea. Didn't leave myself much room. So this is the nickels. And then you got dimes. That's the one we just tacked on here. That's the third factor I tacked on there. So we got 10, we got 20, we got 30, yada yada. You could stop at 100. Yeah, I'm starting to wonder what he meant by, you can dispatch them in a rectangular array. Is this really easier? It's combinations now. It's like you're using all 3 factors. So we still get this one solution. It's c to the 100 times 1 times 1. That's one of them. Yeah. If you're making crazy faces, I don't blame you. So we still have the 21 solutions from here, because that's all this times 1. But now we have a few more. We have like this 10. Oh my god. I should just stop. This is not that interesting. The next question is a lot more interesting than just finishing this out. Yeah, I wonder what his point was. I don't think, because this is much easier what I was doing over here. Like, now I'm doing basically the same thing that I was before with the brute force thing. I'm saying, like, here's 1 dime, here's 2 dimes, etc. You can have all the way up to 10 dimes. But I still have to go back and be like, all right, if there's 10 dimes, then there's nothing else. It's 10 times 1 times 1. If there's 9 dimes, then we still need to make up like a 10. So it's definitely not faster than my brute force method before. I just don't see it being faster. Right? I can't see a way around it. So like, if you went with d is 9, we go back here and we say, like, how many ways can you get 10 more cents out of both of these guys? Well, I guess there's 3 ways. You don't have to worry about pennies, because if you count this, that includes the pennies case, this number 1. So there's like 3 ways for you to make change for 10 cents using nickels and pennies. And then we have the d equals 8 case coming from this power, c to the 80. And so how many ways can I make 20, and you're going to get, I guess, 5 ways, right? So 3 ways for 10 cents, 5 ways for 20 cents. Anyway, I'm going to stop now because this is not faster, but you can see it's more elegant. I don't know if it's faster, but it's it's interesting that you get this one function. Like, this is a function whose coefficients in the power series are the number of ways to make change for that particular index. It's pretty cool. But if you still, if you wanted to just solve one particular answer, I don't know why you would do that. All right, let me move on to number 3 instead of getting burnt out on this counting thing. I'll certainly let you know if I find a more clever way to compute those numbers, but I don't think I'm gonna. I'll ask ChatGPT or something. So number 3, how many ways can you put stamps in one row? So I think they mean immediately, yeah, different arrangements are different ways. So they're talking about permutations now. Notice, like the previous one, we were not talking about permutations. We meant combinations. Like, the order of the change doesn't matter. But here it matters. On 3, they're saying, so how many ways can you put stamps in one row? Postage is 10 cents. Wow. What year was this? This is printed in 78, but the book is from... Oh, maybe it's 72. Maybe it's 72. I thought it was older than that. Yeah, 24. 1924. That makes more sense. Yeah, that makes much more sense. This photograph's from 1925. Oop, you can't see it. This photograph is from 1925 of Polya and Szegő. So yeah, this book's from 1924. It was reprinted in 78, 72. Looks like this one was translated in 1970. But anyway, let me get back to the question. You able to see this? Yeah, okay. So I'm looking at number 3. How many ways can you put stamps down in one row? To make 10 cents worth, you're allowed to use 2, 4, 6, or 8. So obviously, off the top of my head, you could put a 2 and an 8, or you could put an 8 and a 2. That's 2 different ways. You could also do 4 and 6, or 6 and 4, or like different, you could do 6 with the 2s. So we could just count that. But I'm pretty sure number 4, you can see there already, you can't see it. Here it is. We call Bn the number of possible sums to a value n, where the terms are 1, 2, 3, or 4. They're going to do something. He's going to generalize number 3 again. So our first part is just if you had stamps that had these values, how many ways can you I want to say arrange them. Oh, you can't see this, sorry. I forgot to change my focus. There we go. To make 10 cents. Oh yeah, hey, Retromeld, this is actually on, it's on archive.org. Yeah. I don't think the second volume is, but at least this first volume is. There's 2 volumes of this book. So yeah, I probably should have said that at the beginning of this video, but you can find this book on archive.org. But I bought a copy of it because I'm just a dork. I bought a used copy. It wasn't used at all, actually. So yeah, we can just answer this super quickly, but 4 is gonna, let me give you a little sneak peek. 4 says, we call Bn the number of all possible sums with value n. So let Bn represent the number of all possible sums whose terms are 1, 2, 3, or 4. Number of possible sums to value n whose terms can only be 1, 2, 3, or 4. 1, 2, 3, or 4. Those are the only values allowed. And then two sums consisting of the same term. You can't read this. There we go. The same term, I'll just keep it here, I guess. The same term but in different order are regarded as different. And then the question is, of course, the series 1 plus b1 xi plus b2 xi squared, etc. That represents some rational function. What is it? So it's the same as question 2 that we just saw a moment ago. He's basically teaching you how to count and like make generating functions that could help you count these combinations and permutations. Good to see you, Retro. Have a good evening, man. So I'm going to answer this. This will probably be the last thing we look at today. 3 and 4. And they're both very similar to number 1 and 2. So the easy one, this small case, is how many ways can you make this 10 cents? I don't know if I really have an equation in mind for you, because the order matters. So it's not as simple as just saying like 2x plus 4y. But here we go. We have 8 with 2. We have 2 with 8. We have, I'm realizing, well, okay, so that's the smallest set that we could make. We could also do 6 with, oof, this is getting rough, isn't it? You could have 6, 2, 2. I guess this, okay. I'll slow down. 6, 2, 2, or 2, 6, 2, that's different, or 2, 2, 6, that's different. What I was muttering to myself is like, you can't actually distinguish. If I change the order of the 2's, that's not a different arrangement. But okay, we got 3 different ways to get a 6 with some 2's. You could also do 6, 4, right? 6 with 4 or 4 with 6. Those are, so I've got 4 different answers here. Here's one, here's one, here's one, here's one. Here's 3 different answers. And I guess that's it for 6. So are we done with 8 and we're done with 6? Right? I'm glad he only did 10 cents because this would have been a nightmare. How about 4's? If you do 4 and 4 and 2, that'll give you 10 cents. There's a couple ways to do that though. You could put the 2 in different locations. Oops, sorry. 2 or 4. 2 and 4 and 4. So that's another way. There's three more ways to use 1, 2, and 2 4's. But that's not the only combination involving, I should say permutation, involving 4's. You could do 4 with 3 2's. And as you do that, there's going to be 1, 2, 3, 4 different ways to do that. Okay, right? The location of the 4 determines how many. I guess I'll go ahead and do this, but here's other ways to write it. 2 and 2 and 4 and 2, and then finally put the 3 2's first and then put a 4. And are we finally just about done? I guess the last one is just 5 2's. So all these add up to 10. I'm getting an answer like 4 plus 6 plus, so 10 plus another 5. I'm getting 15 as an answer. That feels right. I don't see what I could have missed, right? So let me just double check that I didn't do this easy part wrong already. Yep, 3 is 15. Oops, you can't see it, but 3 is 15. And it's the number of ways. What he mentioned that it's B5 under his notation here. B5 is 15. So Bn, if if you think of a series that uses these number of solutions as the coefficients to some power series, this represents some function of c. It's a rational function, and they want you to find it, the number 4. So you're definitely doing something very similar with the factors, just like before. But this one I don't remember. Also, we want to, we want the order to matter this time, so it's a little more complicated. Okay, first of all, yeah, I just don't remember this one. I was thinking you could raise this whole factor to a power. Yeah, there's definitely a way to do it using powers. I was thinking something like c squared, c cubed, c to the 4. And then we raise this to some power. Right? What happens if we square this, say? Isn't that going to give you it's going to give you every combination. It's going to count this when you get 7. It's going to count that twice. So it gives me all the ways that I could have 2 stamps, right? This is the number of solutions with 2 terms in it. So this gives me some series. Well, I hesitate to put Bn there, but some power series where the Cn's represent a number of sums with 2 terms. And the 2 terms have to be 1, 2, 3, or 4. So when you square this out, you'd get c squared. That's the smallest sum that you can get under these conditions. You only get 1 of those, but then you get c times c squared, and then you also get c squared times c. So you actually get 2 of these, which seems correct. You couldn't get a sum of 3 any other way. You can't even get the value 3. You can if you just had a single term. That's right. You can if you just had a single term. That's interesting. That makes me think we should do something like this. So here's all the ways that you could have just a single term, right? 1, 2, 3, or 4. Then to this I'll add this power. And then to that I'll add the same thing, but with 3 powers, and we just keep going, right? And you can, if you were interested in actually computing this, you could stop at whatever power. So if you wanted, you only want 3 terms, then you may as well stop here. Yeah, how do I... Oh, this is a geometric series, isn't it? It's this number. So it's... I see. If you did this out, you'd get 1 over 1 minus, right? And then you just this term that I've been raising the powers to. So this is the answer. Yeah, that's going to be the answer in the back. Well, that was an interesting one. And it's been about an hour. So I'm going to call it a day. But let me show you what he wrote as an answer before I disappear. The solutions? No, solutions are over here. So for number 3, if you can read this. There we go. So I'm looking at 4. There you go. S terms. See? So if you take like 1, 2, 3, 4, those represent the terms 1, 2, 3, or 4, those powers. And if you take that and raise it to an integer power, or I should say natural number power s, that would represent sums with s terms with values 1, 2, 3, or 4. Now he was saying something further. Specifically, the coefficient c to the n represents ones with value, or sorry, the coefficient in front of that represents the number of sums that you could get using these terms. So you have something like this is this. Oh, I forgot the 1. I forgot the 1. I was off by 1, right? I forgot the 0th power of this geometric series that I wrote down. And then he makes a comment. You can use this relation, which follows from the definition or from this equation. Bn equals n minus 1, n minus 2, n minus 3, n minus 4, summed together. I remember that confusing me, and I don't remember why that's true right at the moment. So this is more or less correct. You know, I'll just say minus. Actually, yeah, I'll just say minus 1. We'll make it match up. But the last thing he says is Bn is Bn minus 1, Bn minus 2, Bn minus 3, and Bn minus 4. I can't just take these out. Like, it's not just 4 separate series. Anyway, see what I'm saying? Sometimes in the solutions, he'll write something, he'll say something like that. That's like a quick one-off comment that is helpful, but it's like not a trivial thing. It's not just obvious. Well, if you think about our previous, we had said B5, and he's claiming, for instance, that B5, of course, B5 is what you'd get if you add B4, B3, B2, B1. B1 has only one way to happen. B2, I guess, has 2 ways. You could have 1 plus 1, or you could just have a single term in your sum. It'd be just the number 2. 3 is a similar thing. It's like 3 1s, or 2 1 1 2. So there's 3 ways already, and then there's one more way. So I think this is it's got to be a 4. Yep. And then obviously this should be 8, but I don't know off the top of my head. 4 could be 4 1s. It could be a 2 with 2 1s. It could be a 3 and a 1. There's 2 ways to do that. It could be just the number 4. There's only one way to do that. And clearly I'm missing some, right? What is this? 5 and getting 7. Am I missing? Yeah, I'm missing something, right? 3, 1, 1, 3. I feel like I'm getting 7. Yeah, I'm definitely getting 7. So I end up with a miscounted somehow. I'm missing one entry on one of these guys. What about 3? Or am I just miscounting? 6, 7. Yeah, I'm getting 14 as an answer, which is wrong. So yeah, how do you get 3 again? Like this or like this? There's 2 ways from that. There's 1 way from that. And then there's just 3, which is 1 way. So I didn't miscount that either. Huh. I wonder what I'm doing wrong. Definitely doing something weird. Yeah, I don't see what I'm missing. Huh. I'm sure as soon as I log off, I'll figure it out. Well, yeah, I'm gonna have to disappear, think about this for a bit. So when I come back, either tomorrow or Monday or something, I'll try to address why this is true. And by then, I'm sure I'll have found this missing number that is driving me crazy. Yeah, I wonder what's going on in my brain here. No, I'm right, it's 15. Hmm. Oh. No, it's not it. Yeah, I don't know what I'm doing wrong here. There's only 2 ways to do this, right? 2 is just a 2, or it's 1 plus 1. Um, yeah, I don't see how I'm miscounting. This is a 4. I mean, this would be the obvious choice for me to miscount, I guess. But I don't think I did. I can't use 3 and 2 to make 4. So it's all 1s. Oh, you idiot. I'm missing it. I'm missing 2 plus 2. There you go. So this is an 8. This is an 8. There we go. Good, 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 good. So that's how you get 15. So there's like one example. This first, the answer to number 3 is one example of this recursive relation being true. But why is that true again? I don't quite remember. If you think, he says it's true both because of this formula and by the definition. Oh, I guess that makes sense. I should probably wait till next time to try and explain it. Like, yeah, okay, so for one, yeah, okay, it is kind of pretty obvious. If you had a sum of n, it could of course just be this plus 1, right? So however many ways you have to create that, which we said was bn, that's one number of ways to make n. Or another way you could get n is by having n minus 2, and you're just going to add the number 2 to it. That's a little fish. Oh, wait a minute. I was going to say you could make this 1 plus 1, but that's not really true, because if you make it plus 1, you could absorb these, and you would have already counted that over here. So don't try to get clever and decompose this 2. Weird. That's weird. Shouldn't there be multiple ways to do that? Yeah, what I was thinking is you can... You can see what I was driving at. I was saying like, oh, I can just say this is n minus 3 plus 3. Or it's n minus 4 plus 4. But like, by that logic, it would just be an infinite sum again. You could be n minus 5 plus 5 too. So why do we stop at 4? Oh, because those are the only terms you can add. You can't add 5. I see. The terms that we were only allowed in this question was 1, 2, 3, or 4. Okay, so are we feeling good about that? This is giving you the number of ways, like basically just add a single term. So like here's the number of ways for you to be forced to add a 2. Here's the number of ways to be forced to add a 3. That's pretty much the gist on that one. I'm just a little curious why the order didn't matter. We've been the whole time we've been very particular about like, oh, if you tack on a 2, like if you tack on a 2 or a 4 or whatever, the order of that matters. So it's like if I put the 2 before or after, shouldn't I get like at least twice as many answers, although you could really put it anywhere. Like for every one of these numbers, I should have another term. And I think it might already take care of that. Well, yeah, so what he meant by it coming from the definition is what I was just saying down here. The other way to observe it would be to use this relation that we discovered between the coefficients and this formula. That I'm not as clear on at the moment. Right? Your suggestion would be like, oh, I can just replace it with this formula and we'll get the same thing. So of course you can split this up. Huh. You end up with like, it's, yeah, I've definitely written this down before. I'm a little rusty right now, but like, if you decompose this now into the four sums, the four series, you could then reapply your formula, except that each time you get like c times your old formula or c squared times your old formula. Um, so it's like this plus c times itself. Actually, I got it wrong. C times this plus c squared times this plus. You basically get this times this old formula. Yeah, I should spell that out a little more clearly, but maybe I'll start the next video with an explanation of this relation. Anyway, thank you for tuning in. That is Dave stumbling through Problems and Theorems and Analysis by Polya and Szego. Have a great day.